Okay, in this segment we're going to be continuing to consider the simple current mirror. We're going to think about, what is this thing good for? What might we want to do with it? And also, what would be the effect of having, let's say, a finite beta? How do base currents come into play here? So if you remember the basic simple current mirror, we had an input current, IN, and it came down into an input transistor Q1. We had an output transistor Q2. And I1 was adjusted to match IN by this diode connection here around Q1. And Q2, by virtue of matching to Q1, produces a copy of the input current. We would call that a mirror copy of the input. So, why would we want to do this? Why is this useful? Well, one thing which may not be apparent is that a current mirror takes what I would call a current source and turns it into a current sink. Right? So this is a current source that is coming down from above. It's dumping current onto the input node. Okay? So it's coming out of here. Whereas if I think about the output voltage here, the output node, Q2 is actually drawing current out of the node. So at Vin, IN is pushing current onto Vin, whereas at the output, Iout is flowing out of the output. And so the current mirror turns a source into a sink. And it's a current source into a current sink. And if we use a complementary type of transistor, if we use a PNP current mirror, that type of current mirror turns a current sink into a current source. So it basically turns around. Turns a current around. And it's maybe easier to see if we think about drawing it like this. So here's our two transistors with the diode connection here, Q1 and Q2. And if we imagine bending these wires and putting a box around our current mirror, IN comes in this way, Iout comes out this way. Right, so it's flowing from left to right here, and it changes this to flowing from right to left on this side. Okay, so that's useful. And if we use an NPN current mirror and a PNP current mirror together, we can build a circuit that basically is able to take a current that flows in either direction and flip it around so that it flows in the opposite direction, regardless of whether it's in or out. So there's ways of doing that. If we can make one copy, could we do something like this? Have a third match transistor, Q3. Let's call this now I2. There's no reason why we couldn't do that. And so if we can make one copy, we could make two copies. Or we could make a Q4 here and make a fourth copy. So we can make multiple copies. Okay, so that may be a useful thing. These are used very often in the context of designing integrated circuits where we're interested in setting up the same current flowing in multiple branches in a circuit, and this sort of thing is very easy to do with a current mirror. Could we, let's go back to the two output one, could we tie these two collectors together? And call this I out? Let's see why not. Well, here I out by KCL is just I2 plus I3, right? Where I2 and I3 are both equal to I1, which is I in, which is equal to 2 times I in. So we have the ability to take an input current and to double it by just having some number of, like, 2 matched transistors on the output side connected together in parallel against 1 on the input side. We could do this, we could take our third one and connect all 3 outputs together and wind up with a current amplifier that amplifies by a factor of 3. If we were to put 2 transistors over here, it turns out we could actually attenuate a current by a particular factor. And so we can scale a current. Accurately, or precisely, let's say. Or no, accurately, I think. Accurately. Okay, so those are some applications of current mirrors that may not have been readily apparent on the initial sort of broaching of the idea. What about the effect of base currents? So let's suppose beta is less than infinity here. So we have our simple current mirror. Let's just go back to two transistors, I in, or I1 and I2. With finite base current, we have basically I'm going to say that this is actually I out, right? Because the 2 collector currents here are what actually match. So when Q1 is matched to Q2, it's the collector currents that are the same. So I'm going to draw this collector current as I out, and this one is I out. So the 2 base currents here are going to each be I out over beta. Right, that's just taking the collector current in each transistor and dividing it by the current gain beta to get the base current. Now the KCL equation at the input node tells us that IN is equal to not just the collector current here, but also the sum of these 2 base currents. So IN is equal to I out plus 2 I out over beta. So we can factor out the I out. One plus 2 over beta. And we can then rearrange this and find that I out is equal to I in times, if I put this over a common denominator, get beta over beta plus 2. Okay. So we get a little bit less output current than we're putting in. If beta is a number like 100, then beta over beta plus 2 would be like 0.98. So if beta is like 100, then I out would be maybe 0.98 times I in. So it's like, a couple percent off systematically. And that's not too bad. That's actually usually quite tolerable. What happens if we have multiple outputs? If we had our 4 transistor output or whatever. Suppose we had Qn plus 1. And the base current here was I out over beta. So we have n plus 1 transistors, each having a little bit of base current stolen from the input KCL. Well, in that case, this is going to be n plus 1 times beta, or n plus 1 times I out over beta. If we have n output currents, and so rearranging, we would find that this is going to be beta over beta plus n plus 1. Right, so if beta is 100, then that is going to set us up with an upper limit on n, right? So if beta is 100, then I out equals 100 over 101 plus n. And if n is, let's say n is 10, well then we're going to have an error that's more like 10%. If n is 100, then we're going to have something like an error that's 50%. And so the number of currents that we can actually, number of copies of an input current we can make here with a multiple output current mirror will be limited depending on how accurate we need those copies to be. So there's a fairly easy, straightforward way to fix this, and that is to have something else supply the input current, or the base current. Right, so one approach would be to just take an op amp, or something like that, and make a buffer out of it so that the op amp supplies the required base currents, and then our KCL equation at the input is just I in is equal to I out, and all of these I outs will now be much better copies of, or much more faithful copies of I in. Right, so find something else to supply all of the required base currents. Now, this may seem fine, But often a current mirror is actually an internal component in making an op-amp. And so you might be wondering, if that's the case, do we have something of an infinite regress here, because we need an op-amp to make a current mirror, which is part of an op-amp? And the answer is no. Sometimes we will make sort of crude op-amps and embed them within fancier op-amps to improve their performance. That's actually done quite often. But another thing we can do, which is fairly effective, if I go back to our two output case here, or two transistor case, Q1 and Q2, I can just use a second, or rather a single NPN transistor, which is basically like an emitter follower. And we'll tie this up to VCC. And what this does is, this is called a beta helper. And it serves as an emitter follower. So remember, the emitter follower we looked at, the emitter follows what the base is doing. So if the base goes up, the emitter goes up. And if the base goes down, the emitter goes down. And here the bias current for this emitter follower is really the sum of these two base currents. Okay? And so this is 2I out over beta. And this, the base current here, would be that divided by beta plus 1. 2I out over beta times beta plus 1. Right, because the base current is 1 over beta plus 1 times the emitter current. And the emitter current is the base currents here. And so we're knocking this base current down by another factor of beta plus 1. So here the KCL at Vn tells us that In equals I out plus 2I out over beta times beta plus 1. And so by rearranging this, we get I out times 1 plus 2 over beta times beta plus 1. And putting that over a common denominator, we get I out equals I in times beta plus 1 over beta times beta plus 1 plus 2. Alright, so if beta is a number like 100, I out will be something like I in times, well, 100 squared, roughly, is going to be 10,000. So 10,000 over 10,002. Which is going to be like point. Something like that. So much closer to 1 than it was before. And so we could actually tolerate quite a few more output copies here than we could without the beta helper. Notice here that the input voltage is not just 1 VBE above ground, now it's 2 VBEs above ground. Okay, so with the beta helper here, we require a slightly higher input voltage. So instead of being typically like 0.6 or 0.5, it's going to be more like 1.2 or 1.1 or 1 volt or something like that. So sometimes we can tolerate that just fine. Other times that can become an issue. But that would be what we would call 2 diode drops above ground, or 2 VBEs above ground instead of 1 VBE above ground. Okay, well that's some applications of the current mirror and the effects of some finite base current and some ways of mitigating the base current. So you basically find something else to supply the base current and prevent that base current from stealing current away from the input KCL equation. That's it for this time, and we'll see you next time.